Hi, my name is Ajay Rao.
And I'm Pranav Moraga.
And I'm Danny Silverstein.
Hi, I'm Pranav Lurie, and what is linear programming?
Hi, I'm Pranav Lurie, and I'm going to be introducing linear programming. So the biggest thing in linear programming is really about optimization. And what this is a method to achieve the best allocation of resources. And these resources can be anything from profit, lowest cost, labor, etc. Basically, anything that has predefined constraints that can restrict resources is a good problem to use optimization to allocate resources in the best possible way. And when multiple variables and constraints are added to problems, it can be quite difficult to determine a corporation or even an individual's best course of action. This is why linear programming is so important, because it can use objective functions and decision variables to best optimize the solution for a given problem. And as you can see in the picture below, the linear equality, so like y is greater than or equal to x minus 2, is a constraint that we might have in the problem. And together, when we take all those constraints, we can use them in linear programming to create the bound region, which is our optimal solution for this problem. So before we go into actually solving these problems, we need to know about the key terms. So in most problems, we start with an objective function. So this is like z equals ax plus by, where z can be something like profit, which we're trying to optimize. Then we have the decision variables, which are x and y. And these variables represent the unknown quantities that will determine that we will determine to optimize the objective function. So if z equals profit, x can equal things like product or labor, and y can also equal product or labor. And then once we have this objective function and the decision variables, we create something called a feasible solution. This is a solution that meets all the constraints for the decision variables, but does not necessarily have to be the most optimal solution. The end goal in your programming should be to create the optimal solution. This is a solution that maximizes profit or minimizes costs or anything else that you want to optimize. This is the best value for the objective function. And what this does is it optimizes the objective function while also satisfying all the constraints, which is really the end goal of linear programming.
All right, this is Danny, and I'm going to be showing how to solve this just generally. So, first method we have is a graphical method. We're told to maximize z equals 3x plus 5y given the two constraints. And what we have to do here is we have to sketch out this the inequalities to see this region here. We're only concerned with where the two inequalities overlap and only in the first quadrant. So that's this region right here. And to determine the candidate points, you could say, we have to find the where it intersects the x-axis and or the y-axis and the x-axis. So we have those 2 points, as well as we need to find when the inequalities intersect. So in this case, I just did a system of equations, REF'd it, and got x equals 10.91 and y equals 13.182. Given these 3 points, the 35 over 2, 0, 0, 125 over 7, and 10.91, comma 13.18, we plug it back into the equation of z equals 3x plus 5y and determine whichever output is greatest. In this case, it's the 98.63. So our maximum is at 10.91, comma 13.18. There's also the simplex tableau method. This is more commonly used because it's easier to use in computers. So we're told to maximize. Similar thing to before, we're going to graph out the region. And this region is called the region of feasible solutions. So our optimal solution would be somewhere in there. And using the simplex tableau method, we're going to use things called slack variables. These are basically just any real number that turns that inequality of 3x plus 5y is less than or equal to 78, for example, into 3x plus 5y plus s1, which is our first slack variable, equal to 78. So it takes away the inequality and makes it inequality. So to do this, we set up a matrix of sorts with the constraints, and the last row is the equation that you're trying to maximize. So you can see I shifted the 5x and 4y over because we need p to be positive. You'll see why later. So what we have to do here is we divide the leftmost component by the rightmost component. So 78 divided by 3, 36 divided by 4. We only do this for the first 2 rows. And whichever value is smaller, in this case is 36 divided by 4, that's the row that we're trying to get a leading 1 in first. So we want this 4 to become a 1. We want the 3 and the negative 5 to become zeros. So that's just elementary row operations. And then we're left with this right here. we're going to keep doing this process over and over until we can see this last row has no negative numbers in it. So you can see there's still negative 11 and 4, so we got to keep going. Same thing, 51 over 17 over 4, and 9 over 1 over 4. The 17 over 4 is smaller. So we're going to make that a 1, and the 1/4 is 0, and then negative 11/4 is 0. Same thing, elementary row operations, and we're left with this. This is, we have no negative numbers there in the last row, so we're done. And the way that we read this is we look for the first leading one, and that's in the y component, and that's equal to the component in the last column. So y equals 12, there's a leading one here, x equals 6, first leading one is here, p equals 78. That's our maximal solution, and we just say the slack variables are equal to 0. There's also minimizing, however, and this is a bit more complicated. In minimizing, we actually have to make it a maximizing problem of sorts. So we're going to set up this matrix with the constraints and the equation we're trying to minimize. So you can see here just 60, 60, 30, 12, 6, 36, 10, 30, 90, and then we make the 0.12, 0.15, and 0. We set it equal to 0. And to maximize this, we're going to take the transpose first, leaving us with this, and then we write our new equations and treat it like a maximization problem. So z is equal to this last row, the three-dimensional y1 plus 36 y2 plus 90 y3, and then our constraints are these first two rows, less than or equal to 0.12 and less than or equal to 0.15.
Hi, my name is Pranav Mariga, and let's get into an example of what was previously stated in the previous part. So in this case, we have C/Bakery. It's a bakery that produces muffins and cakes, but its only resources are labor and dough. And now we're trying to maximize the amount of revenue using the limited amount of resources we have to their maximum potential to get the maximum amount of products and revenue possible. So we only have 40 hours of labor in a workday with 120 pounds of dough to work with. So let's define our variables. X is the number of muffins and Y is the number of cakes. Our objective function is z is equal to 40x plus 50y, and our constraints are as follows. Since this is a maximization problem, we have to make them less than or equal to 40, less than or equal to 120. So this is one way of solving it, is using a graphical solution. We simply graph out our constraints, and using the area under, we're able to see what is the most reasonable and optimal solutions for our revenue. In this case, at the y-axis, we have z is equal to $1,000 versus the x-axis where z is equal to $1,200 for different maximum amounts of the product made. But at point B, where we have 24 muffins and 8 cakes, that's the most amount of revenue possible with $1,360. That is us using optimal amount of resources to make the optimal amount of products to make the maximized amount of revenue. Now let me go in depth about the simplex tabloid. This is another way of solving the very same problem, as Danny stated in the previous part as well. So we have our objective function and our constraints, and we are adding our slack variables. These will be able to turn the inequalities into equations that we can use to put into our simplex tabloid. Simply put, we have negatives on the bottom row, and we have to get those into non-negative form to get our maximized z. So we simply find our entering variable, which is the least value on the bottom row, and we find our departing value, which will have the smallest ratio with b, which is going to be at 20, and that will be as y is the entering variable and s1 is the departing variable. So simply doing elementary matrices and operations, we're able to get a new simplex tabloid, and now we need to still get the negative 15 out of there, and so negative 15 or x is our entering variable with s2 being our departing variable. So we repeat the same process, and we're able to get $1,360 as our maximized revenue with y equal to 8 cakes, and 24 muffins. And to test this out, once again, we just plug those values into our constraints, and we were able to get them to match within the constraints. So thank you. This is one of two ways of getting the maximized revenue through the most optimal means. Now, let's go in depth about mixed constraints. I just talked about maximized constraints, and in the previous part, we talked a bit about minimized constraints. Now, in mixed constraints, there's going to be a mix of both, as shown. With our objective function right here, as you see, there's a less than or equal to. This is a minimized, and this is also a minimized, where it has to be greater than or equal to 36 and 10, respectively. There, you're going to add your slack variable, and you're going to add your surplus variables. These are variables that will add a surplus to get us to 36 and 10, or subtract 2, and they have to be non-negative. This is very important. So when we're doing a simplex tabloid, is simply all non-negatives in the bottom, and we have to get that out doing simple operations as stated before. And as you can see, the current equation of points does not work because our surplus variables are non-negative, and this cannot be an optimal solution. Thank you for your time, and I'm going to leave it to Ajay to talk about applications.
Next, I'll talk about the applications of linear programming. Linear programming is a method for optimizing operations with respect to certain constraints. Therefore, it's used to make processes more efficient and cost-effective within several industries. One of these industries is the food and agricultural industry, which we walk you through a problem for. It's also used in transportation to make a lot of our transportation more time and cost-effective. And finally, it's used in manufacturing to let firms know what product to produce and how much of it to produce as well. These are only a few ways that linear programming is used, but it's used in several other areas as well. Thank you for listening to our presentation.